That
Addition
is
of
the
hydrogen, right?
addition of HX. Yeah, HF, HCl, HBr, HI. Right. Okay. And you have a double bond. And what's the mechanism? Actually, this is electrophilic addition reaction. Okay, because the HCl which you take dissociates into H plus and Cl minus. Right.
Yes, sir.
Now the next thing is who comes and join on the double bond first. It is the H plus. It is because your alkene just it is because alkene has pi electron density above and below the molecular plane. Okay, the pi electron is like this. Sigma electron, the single bond is sigma, and the electron density of the single bond is actually in the plane of the molecule, and the pi electrons are actually formed by p or by t. Okay, you must have studied in class 11th, and their electron density is above and below. So what happens is H plus is an electrophile, Cl minus is a nucleophile. Okay, so what happens here is the H plus comes and get attracted toward the pi electron, right?
Yes, sir.
So what H plus do is H plus try to accept the electron from the pi bond. Okay, H plus want to accept the electron from the pi bond. So that's why an H plus is an electron loving species, and that's why the name electrophilic addition reaction. So I will write here the Cl minus can't come and join itself directly to the double bond because the double bond has pi electrons and the Cl minus is also electron rich. It is minus. So the H plus will come and join. So H plus will come and take the electron density. Just note down the arrow. Arrow I put, where do I put arrow? From the source of the electron to the destination. Okay.
Yes, sir.
So what I get this one. The electrons which were in the pi bond, now they are taken by H, and H has joined itself to the one of the carbon atom, leaving a positive charge on the adjacent carbon atom. And now the Cl minus will come and join itself to this because this carbon atom plus charge is unstable, so Cl minus can come and give its electron pair, and that's how it can make this C plus stable. Okay, so this is the final answer. So two things are getting added to the double bond, and this is electrophilic addition reaction. So here you can see this is addition of HBr. So you have one at one position H and another position Br added. This is addition of HI. One at one H is, it is not represented in bond line representation. If you want, we can write. Okay, to make it more clear. Okay. So all of these alkenes which were given, they were symmetrical alkenes. And you don't have to think where you should put H plus, where you should put Cl minus, that you don't have to think because it was same from both the sides. Okay. Now the problem comes when you need to attach HCl to an unsymmetrical molecule. Like this one. This molecule is unsymmetrical. This is not symmetrical. As you can see, this side and the other side are different. Now, where do I need to put H plus? Any idea? Tell me.
The carbon of the double bond, which is having lesser number of, which is having greater number of hydrogen atoms.
Yeah, greater number of hydrogen. Rich gets richer. Okay, this is the shortcut way, shortcut trick to remember. Yeah, but why Is it so? What is the reason actually? And this is the correct answer. H will attach itself to the carbon atom bearing more number of hydrogen. But what is the actual reason? Yeah, tell me. Reason is the stability of the cation. Okay. So
Yes,
suppose if the H plus is coming and joining from the right hand side, the double bond which is like this in the middle, it will become like this. Okay, like this. So plus charge will come on this card. That is the first case. Okay. And the second case is if the H plus comes from the left hand side, the double bond will get shifted down and the plus charge. This is the second case. Okay. So as you told me, correct, that we need to do the first case. What this rule is known as? What this type of addition is known as?
anti-Markovnikov rule.
No, this is Markovnikov. Normal. Rich gets richer is Markovnikov. This is Markovnikov addition, right? So rich gets richer, the plus charge, and it is governed by the stability of carbocation. So if you proceed, this carbocation is tertiary carbocation, and this is primary. What is tertiary? What is primary?
Carbon attached to 3 other carbons is tertiary.
That is
Where
tertiary. Yeah.
if it is
Connected
attached
to
to
one
only one
carbon.
carbon atom, then it is primary.
Yeah, primary. So the tertiary more branched the carbocation is more stable it will be. So this is going to be the major product, and this is formed by the way in which you add H plus to the carbon atom which has more H. So this is Markovnikov addition, and this one is minor product. Okay, anti-Markovnikov. So suppose if someone asks you to write the product, you will write the Markovnikov product only. Okay, this one has a major product. Okay. So why tertiary carbocation is stable? What is the reason, Nabil? Tertiary carbocation, what is the why it is more stable? Why we are, because it is more stable, it can form more easily. And this is less stable, so it will form with difficulty, it has more energy. So the reason for stability is what? It is actually the branching. First of all, the alkyl groups are not electron pulling. They are electron giving groups, electron donating groups. Okay, so if you have a tertiary carbocation, it means the carbon needs electron because it has a plus charge. Carbon doesn't have electron. Carbon need electron. So carbon need electron, and these are alkyl groups, small alkyl groups, and they are not very electronegative. They can push the electron pair towards the carbocation. That is one reason. Another reason is this: there is one more way by which this carbocation, that these electron can also come and temporarily get joined themselves to the C plus. And this effect is known as hyperconjugation. Okay. So it is just like the carbocation is there. It is a carbon which doesn't have any electron. So if you have 3 alkyl groups surrounding that carbocation, those alkyl groups have CH bond, and those CH bond can give their electron to the C plus temporarily, not permanently. Suppose if you forget to take your lunch box in your school or your picnic, so what happens? Your friends may share their lunch box with you. Okay. So same way, a tertiary carbocation is more stable, right? Then secondary, in primary, and what is the governing factor for Marconi addition? Actually, you need to attach H plus on the double bond in such a way so that a more stable carbocation is formed. Out of the two carbocation which are possible, a more stable carbocation can form. That you need to think. Okay, clear?
Yes, sir.
So this one, Marconi addition of HI, how you are going to do it? This does not have any hydrogen. This has one hydrogen, so you are going to put H here and I in this case. So this will be the major product, right? This
Yes,
is the
sir.
Marconi of. So you are going to attach the nucleophile to the carbon atom which is more branched. In this, if you think this is H already there. Okay, so where the H plus is going to come and attach, H plus will come and attach itself to the. So this you will have C plus over here. Okay, I will write it above separately. One H was already there. Another H from HBr came and joined to the double bond, pulling the pi bond outside. Then you have a carbocation on more branched carbon atom. That's what we want, because carbocation on more branched carbon atom is going to be more stable. So this is Marconi competition, and BR you are going to join here. So this is the major product. So sir, if someone asks you write the product, always write the major product. Okay, don't write the minor product at all. But because we need to discuss, that's why we are writing showing the minor product. This is anti-Markovnikov. Normally this will not form. You will write the Markovnikov addition product only. Okay, that is going to be the final answer. Okay, and what will happen in this? Just give it a try. What is the IUPAC name of the product in this? Yeah, Nabil. Any idea? So first you have to do Markovnikov addition.
Sir, 2 bromo 3 methyl butene.
Yeah, but you need to be careful about one more thing. You have done half of the thing correct, but you forget to do one more thing. Okay, this is the carbocation, and you attach the BRA. Okay, that's what you did. So you did half of the part correctly, but actually what happens is carbocations have a tendency. Remember, everywhere, not only in this chapter, in all the subsequent chapters which are yet to come in organic chemistry, remember carbocations have a tendency to undergo rearrangement. Means they can, if the carbocation is formed on this carbon, it can get shifted to neighboring carbon atom if it is becoming more stable. If, but this will happen only if there is increase in stability, then only it will happen. So let's see, will it happen in this case? This is secondary carbocation, and if somehow carbocation can come on this carbon, this will become tertiary. So do you want the carbocation to get shifted to the neighboring carbon atom? Do we want it or not? What could be
Yes.
the option? Yes, because the carbocation will become more stable. It will become tertiary. Yeah, so we need to shift it. But now the thing is, who will get shifted on this position where the carbocation is already present? Because some of the group has to go and along with its electron to that carbocation to the position where the original carbocation is present. Okay, so actually this will be as per migratory aptitude. The migratory aptitude of H minus is maximum followed by pH. Okay, followed by tertiary carbon, followed by secondary, and followed by 1 degree. So on the adjacent carbon, I will write once again how many groups you have. How many groups you have? You have 3 groups on the adjacent carbon. 2 of them are methyl, 1 is hydrogen. So out of methyl, hydrogen is having more migration tendency. This is known as migratory aptitude. Okay. So this is the detailed discussion. So you need to shift this H along with the electron pair to that carbocation. So you will have a new carbocation which is like this. Okay, this is a tertiary carbocation. Or simply what you can think is that you can make tertiary by removing H. That's only a basic method. So if you have a tertiary carbocation, this is called rearrangement of carbocation. Okay, this is called rearrangement of carbocation. And now once the carbocation is finally, it is rearranged, it has become more stable. Now you can join the Br minus here. Is it clear?
Yes, sir.
So you should be careful about the rearrangement of carbocation. It is very, very important. Look here how it has happened. The whole, so major product is Markovnikov of addition. That's true. But if there is a possible, so you first attach H plus so that a more stable carbocation is formed by attaching H, and that is attained by attaching H plus to the carbon atom bearing more number of hydrogens. Once a carbocation is formed, you will check that is this carbocation will get shifted to the adjacent carbon. If yes, you will do the shift. Okay, you will make the carbocation more stable. Okay, look here. This was secondary. Now this is tertiary. Once it has become more stable, then you will attach the Br minus to write your final product. Okay, but so be careful about the rearrangements. Clear? Okay. So there is one more way of addition, and that is anti-Markovnikov addition. That can also happen. Okay. Anti-Markovnikov addition can also happen. Okay. So when anti-Markovnikov addition happens, and with whom it happens? Yeah. Among HX. So among all HX means HF, HCl, HBr, and HI. Only HBr can show anti-Markovnikov addition. Only HBr can show anti-Markovnikov addition. Clear?
Yes, sir.
And that too in the presence of peroxide. Only HBr can show. What are peroxides?
Sir, H2O2 like that.
Yeah. So H2O2, yeah, there are other kind of peroxide also. For example, benzoyl peroxide is there, that is very famous. Because it can actually, these peroxides have O bond, and this O bond have lone pair. So because oxygen have lone pair, so upon giving slight amount of heat or light, it can break very easily and it can generate radical. Okay, so this is a free radical. So peroxides can change the way of addition of HBr. Okay, is it clear? So anti-Markovnikov addition is shown by HBr only. HF, HCl, HI. They will not show anti-Markovnikov addition, means even if you take peroxide, they will add in a way in which they were adding without peroxide. Their addition will not be affected by the presence or absence of peroxide. Only HBr way of addition will get reversed in the presence of peroxide. Okay. So normally how HBr adds? Normally HBr adds in a Markovnikov way, in which the H plus attaches itself to CH2 and the Br minus attach itself to the less more branched carbon, okay, where the carbocation is stable. So this is Markovnikov addition, but in the peroxide, the way of addition of HBr is reversed. You can see over here. Okay. So this is the carbon having 2 hydrogen, but I will not put hydrogen over here. I will put hydrogen at this point. Instead, I will put Br in this at this carbon. So this is the reverse addition, and this is the anti-Markovnikov addition of HBr in the presence of peroxide. So it is known as peroxide effect, anti-Markovnikov addition, and this is also known as Kharash effect. Because of the name of the scientist who studied this experiment. Okay. And this is free radical addition. So actually, in simply, if you take HBr, H plus was playing a major role, and that was going HBr dissociated into H plus and Br minus. H plus was going and taking the electron pair of the double bond. The double bond was getting the plus charge, and the Br minus was forming. So this was electrophilic addition reaction because the addition was initiated by H plus, which was an electrophile, right? But in the presence of peroxide, the mode of addition changes. It becomes free radical addition because peroxide actually breaks very easily by sunlight or something, by heating, and peroxide gives you species having unpaired electron. Those are known as free radical. So if HBr comes in contact with this peroxy radical, they will break the H radical, PHCOOH, and the Br radical will be. So Br radical comes and join. So that is a thing. If someone asks you about the mechanism, that also we will do. But as of now, you can answer this question. You can tell me the IUPAC name of the products. Yeah. And they are asked everywhere in all the examination. So first one. Yeah, Nabil. Peroxide is there. So what do I need to write here? Is this the answer?
Yes, sir.
For this one?
sir, the first one.
Peroxide is there with HBr. So if peroxide is there, addition will get reversed. Okay.
Yes, sir.
So normally addition, how it occurs? It occurs by when H plus add itself to the double bond, bearing more hydrogen. Okay, and then the Br comes and joins in this way, right?
Yes, sir.
So this was Marconic of addition. But in peroxide, the mode of addition is going to change, and this will be the answer. Anti-Marconic of addition. This is the answer. Is it clear?
Yes, sir.
The 2-bromo 2-methyl. So mode of addition of HBr reversed in the presence of peroxide. So now the H was not attaching itself to the carbon atom, which is having more hydrogens. Instead, H was attaching itself to the carbon atom, where earlier Br was used to get connect itself. And now the Br will come in. Okay, right? And for this one, what will be the answer? Simply if you take HBr.
The first one, sir.
Yeah, that is first one. Yeah, correct. 1-bromo, 1-methyl cyclohexane, and in this case, the answer is 1-bromo, 2-methyl. I need to give 1,2-bromo because it is alphabetical sequence. It comes before M. 1-bromo, 2-methyl cyclohexane. Yeah. And what about this one? HCl is there and peroxide is there. Yeah. What do you think? Is the addition of HCl?
It's not possible, right, sir?
Yeah, it doesn't get affected. It doesn't get affected. HCl is going to attach in a way in which it was doing without peroxide. Normal addition. Okay. So anti-Marconic of addition is not possible. Okay. Simply you will attach the HCl in a way in which it was getting attached earlier, right? So here you can see how many hydrogens are there at this position. How many hydrogens are there? 1 hydrogen, right?
Yes. Yes, sir.
Yeah, you can count the number of bonds 1, 2, and 3. So carbon make 4 bonds. If there are 3 bonds, that means 1 is hydrogen. Okay. Okay. Right. So H plus will come and join itself to the position where H plus is already there. And the Cl minus will come and join to the carbon atom which is more branched. Okay. So this is the answer. Clear?
Yes, sir.
Okay. So why anti-Marconic of addition occur? So normally HBr without peroxide. It breaks into H plus and Br minus, and on the double bond, the H plus approaches the double bond because H plus is an electrophile, it needs electron, so it approaches the double bond and takes away the electron in a way such that it gives a more stable carbocation. The carbocation will come in the middle, and there the Br minus will go and join itself. This was electrophilic addition reaction, because H plus was an electrophilic species, electron loving species, and that was going and getting attached to the double bond. Okay. But what happens in the presence of peroxide? Actually, just now I told you that peroxide have OO bond, which is very weak, and it get broken into O radical. Radical means single unpaired electron. Okay, and it get broken into radical by heating or by light, and this O radical goes and interact with HBr, and because it is already having one electron. So when it reacts with HBr, it takes away the H with one electron only, because the one electron already oxygen is having. So if it bond itself to the hydrogen, so it will bond itself with the hydrogen radical. Okay. So normally this hydrogen radical, actually it is shown here that it is S radical and Br radical. But who is responsible for taking away the H radical? The peroxide. And the Br radical left alone. It is left alone. And it is not going to stay as it is, because it is an intermediate. It has unpaired electrons. You can see. So unpaired electrons. So Br radical is not going to stay as it is. It is unstable, and it somehow or the other it will try to join itself to some other molecule which are present in the system. So in the system we have taken alkene. On alkene, Br radical will come, and it will interact with the pi electrons of alkene, because pi electrons can be taken away very easily. But because Br is having one electron, so it will come and join itself to the pi electron by taking only one electron. Okay, the other electron will remain on the carbon only. Okay, so Br will join itself. So now here again the question comes, pi electrons are present on both the carbon on CH2 and CH. So where the Br radical will attach itself? The answer again is same. Okay, you need to consider the stability. So the Br radical will join itself such that a more stable radical is formed. So if the Br radical join itself to the outer carbon, okay, the radical will form on the inner carbon, which is secondary, which is more branched. So this is more stable. But if Br radical try to join itself on the inner carbon, the radical will come on the outer carbon, which is 1 degree. That is not very stable. So this one is preferred, and this one is not preferred. Okay, this one is not preferred, and this one is preferred.
So can you say some why again?
Yeah. So Br radical will come and join to the double bond. Okay.
Yes, sir.
And it will take only one electron from the double bond. Reason is Br is already having one electron. You can see.
Yes, sir.
So to which atom the Br will join itself? Where the Br will come and join itself? On this one or this
Second
one?
one, right?
On CH2 on CH.
CH1, CH, right?
If the Br comes and join itself on the CH, the radical is left on CH2. But if the Br comes and join itself to the CH2, the radical actually comes on this one. Okay.
Sir, but CH2's radical can't go by taking up a hydrogen.
No, this radical is more stable, no, because it is secondary,
Okay, sir.
right? It is overall we are doing anti-Markovnikov addition, but we need to understand why it is anti-Markovnikov and why that was Markovnikov. That was Markovnikov because H plus was coming and getting attached to the double bond. and there the plus was forming, and the plus. So there we were concerned about the stability of the C plus, which was formed after the addition of H plus. Okay, but here we are concerned about the stability of C radical, which is formed after the attachment of Br radical. But how Br radical came? It was, who is responsible? The peroxide. The peroxide actually itself broken into O radical, and that O radical has taken away the H radical, and that's how the Br radical is generated. And Br radical will attach itself to the double bond, leaving behind a C radical. So now in this case, we are concerned about the stability of the C radical. So we need to attach Br radical in such a way such that the C radical which is forming should be more branched. Okay. So I made C radical inside, not this one, as this was less stable. Okay. And now what will happen? This C radical will again react with HBr, and it will break away the H radical, and that's how the overall reaction gave a different product in the presence of peroxide. Okay, different from what we were getting without peroxide. Okay, clear? Any doubts you can share? You can tell me anytime. Yeah.
Yes, sir. Yeah.
Okay. So
So the
you
last
are
point is one more time, sir. 1 second.
yeah, pardon.
Last point is shown.
Last point. Should I explain again?
So just 1 minute, sir. I'll just write it down.
Yeah, yeah. You can write it down. Yeah, do write it down. Actually, these things are very volatile. Actually, I remember from my days when I was preparing for JEE at that time, and this was a very confusing thing for me. Okay, so you need to write and practice it 2-3 times. You will be 100% sure. Okay.
Yes, sir.
Yeah. So shall we proceed?
Yes, sir.
Okay. So this one. So what's going to be the answer for this reaction?
Sir, the third one.
Yeah, this is anti-Markovnikov addition of HBr because peroxide is taken. So normal addition is rich gets richer. This was the normal Markovnikov addition. Markovnikov addition occurs if you take only HBr. Normal Markovnikov addition occurs only with HBr. But have we taken only HBr?
No, sir.
What else we have taken? What is this?
Peroxide.
Yeah, this is benzoyl peroxide.
Sir, how do you know difference between peroxide and anhydride?
Anhydride actually is this one.
Okay, sir.
There is only one oxygen. This is benzoic anhydride. And this is benzoyl peroxide.
So it depends upon oxygen number, sir.
Yeah, the middle oxygen. Peroxide have that O linkage. So these peroxide actually with light they break very easily to give O radical. That O radical takes the H and gives you Br radical. The Br radical will join itself to the double bond such that a radical is formed on the inner carbon, and there the H get connected. So first the Br radical you need to think of this addition of Br radical, then attach H. Okay. So Br radical will join itself outside such that the carbon radical is formed inside, and then at inside you will attach H. Okay, Br and H. So this is going to be the answer, right? A.
Yes.
So you are preparing for NEET or means? I forgot actually. You told me earlier.
Means G.
Yeah, JEE. So this is an important question. Okay. And the another thing is, before moving ahead, why only HBr shows anti-Marconi of addition with peroxide? Why can't HCl, HF or HI show anti-Marconi of addition? That is the next question. What is the reason? Yeah, tell me. This has also been asked in JEE. Actually, there is a question based on this, and this was the question when I appeared for JEE. Okay. But a very good question, very basic question. So HCl is taken and peroxide is taken, you can see here. And they are asking you what is the intermediate form. Okay, what is going to be the intermediate formed in this reaction? This was in JEE advanced. Yeah. But a very simple question. Now it can come at any level. What is the intermediate formed when HCl is added in the presence of peroxide to propene?
Sir, fourth one, sir.
Fourth one. Yeah, first of all, we need to know. We need to write. We need to know. We need to. You can write that HCl will HF, HCl, and HI will never show peroxide effect even if you have taken peroxide. their addition is not going to get affected by peroxide. They will always give Markovnikov addition. Always Markovnikov, right?
Yes, sir.
You can write that. Okay. So if it is Markovnikov, if it is unaffected by the peroxide, peroxide can't do anything to HCl. HF, HCl and HI, they will add in a way in which they were adding without peroxide. Okay, and without peroxide, how they were adding H plus and Cl minus. So what you need to think in your mind, H plus, okay? Clear?
Yes, sir.
So H plus, where the H plus will attach itself? Rich gets richer. Okay, this one, cation will come on the inner carbon, secondary cation. So this is going to be the answer. Okay, clear?
Yes, sir.
And all these will not be the answer because HCl doesn't get affected. So I hope this is clear. But actually in examination, most of the students first time make mistake. Even I also made the mistake. This was a question from my time. Okay, in my JEE, I did this question. Okay, just after the paper, I realized that it was wrong. I made a mistake. Okay, in examination, actually everybody do this mistake. Okay, so be careful. So so another thing is, what is the reason why? So in JEE, actually 2 or 3 times the reason is also asked. Okay, so what is the reason? The reason is HF and HCl have strong bond. Okay, and they are not cleaved by peroxide. Look here, what the peroxide is doing. The peroxide is breaking the S radical from the HBr. And why the peroxide is able to do so? Because the HBr has weak bond. For HF and HCl, the bond is strong. You can write the reason. Don't give peroxide addition because HF HCl bond is not cleaved by peroxide. Okay.
So for HI also, sir.
No. For HI, there is a different reason. HI bond is going to be very weak because hydrogen is the first period element, which is very small, and I is the fifth period element, which is very big. So the bond is going to be very large. It is going to be very weak. So HI will be very, 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 very easily cleaved by the peroxide. Okay. So then what is the problem? If it is cleaved very easily by the peroxide, then why it is not giving peroxide addition? Why it is not giving anti-Markovnikov addition? The reason is, so first step is, you can see over here, the peroxide break the H radical and leaves Br radical. So first step was not possible in HF and HCl. So, and sometimes it is said that the first step will have positive delta H, means you need to give energy for HF and HCl because their bond is strong, so that will not happen. So delta H positive, it is also said in this way, or means they can't add because they have their strong bond. Okay, but HI, this is not the case. HI bond is very weak. It can get cleaved into I radical very easily by the peroxide. But what happens is, if the I radical form, the I radical is very big, and that single electron is actually, the electron cloud is spread over a very large atomic orbital, that is 5p. Okay, and if it is spread over a very large atomic orbital, it cannot form a bond effectively. So just the generation of I radical is not enough. Now the next challenge for the I radical will be to go and attack on the double bond. The Br also did the same thing, but I radical can form very easily because HI bond is very weak. But I radical is formed, but it will not go and attack on the alkene because I radical is very large and it is very stable. It will not attach itself to the double. That's why the HI will not show peroxide effect, but HI adds to the double bond as H plus and I minus. Okay, H plus and I minus in a normal way, the way in which we have seen here, in a normal way, H plus and, so normal way is H plus and Br minus, H plus and Cl minus, H plus and I minus, so H plus will go and attack on the double bond. Okay, that is the normal way. But in peroxide, the some new intermediates will form, but that is only for HBr, not for HF, HCl, and HI. HF, HCl, and HI they are going to add in a way in which they were doing without peroxide, means H plus and Cl minus, H plus and I minus, because peroxide can't change their mode of addition. HF and HCl are not cleaved by peroxide in homolytic way. Homolytic means radical are formed equal distribution of electron. On the other hand, HI is cleaved very easily by the peroxide. By I radical being very large and very stable will not go and add to the double bond. So we need to break HI in the way in which we were breaking earlier. H plus and I minus, and H plus used to go and attack on the double bond, and I minus used to go and attach itself to the carbonate. Is it clear?
Yes, sir.
Okay. Yeah. So now this is the way in which you can prepare the alkyl halide from alkanes. Alkanes, the method was photohalogenation. Okay, you must have remembered that we did photohalogenation long back. Okay, not this one. I think that was in previous slide. So photohalogenation we did. Okay, by alkanes. But in alkenes you need to take HBr. HBr you can H, but alkene it is electrophilic addition. But with electrophilic addition you have freedom with HBr that you can attach it in a way you want. Okay, but that freedom is not there with HCl and HI, right? That's what we discussed. Now, how do you prepare aromatic halides? That's the question. Okay, so what do you think? You can tell me first. So how do you put some group to the benzene? So first of all, before discussing anything, benzene is an aromatic compound. What do you understand by aromatic compound?
Smell. It is having a ring.
Yeah, it is having smell, aroma, but that concept is there, but we need to understand it with the help of stabilization. Actually, aromatic compounds have 4n plus 2 electrons, okay, in a cyclic manner. Mean double bond, single bond, double bond, and there are 4n plus 2. 4n plus 2 is a general term. Means you have 6 electron, you have 10 electron, alternate double single bond. So what they do actually being neighbor actually. So this is the diagram of benzene. So these are p orbitals. So you have sigma bonds, but you have electrons in the p orbitals, and those p orbitals actually they form 3 double bond. But these p orbitals actually not join only on one side, actually they overlap in all the sides. Because they are all neighbors. What benefit will it give? That will make the 6 pi electrons to move throughout the ring. And this phenomena is known as what? Tell me. Yeah, Nabil. This phenomena is known as resonance. Okay. So aromatic compound have aroma. Naphthalene we put in our as moth balls in cloth. Okay, they have that aroma. But the more important concept is they are aromatic compound. They are stabilized by the cyclic resonance of 4n plus 2 electrons. They are very stable. And the stability is because the pi electrons are in a cyclic order and they join, they are neighbors, they join with one another, and that's how they let the 6 electrons to move in the ring. Okay.
Yes, sir.
Clear.
Sir,
So
and 4n plus 2, it is, what does n stand for, sir?
n stand, you can, that is a general way. N doesn't stand for anything. N is a whole number. That will give a general idea of, you can put this whole number as 0, 1, 2. You will get a series of pi electron, and you need to know that your molecule should have any of these number of pi electron to become aromatic.
Sir.
For example, if you take n as 0, so it will be 2 pi electrons. So this is also aromatic compound. Okay, the 2 electrons are like this. Pi electron, they can go like this towards the positive charge. The positive charge will come here. Okay, then they can come like this. The positive charge will come here. So actually, the 2 electrons are moving in a cyclic manner. So this is also aromatic. Normally, a cation is very unstable. But in this case, this cation is very stable. It can continue to stay as it is. Normally, we never stop at cation in organic chemistry. Okay, we join, just now we have seen in Markovnikov addition, we were getting cations, and the cations were attacked by Cl minus or Br minus. And we were getting the neutral product. But in this case, the cation is very stable because it is aromatic. So there are many aromatic compounds. The benzene is the most common. And why I am discussing the aromatic nature here, because this cyclic resonance, cyclic movement of 6 electrons means stability. Okay. And while doing the reaction, we need to be careful that this stability should be maintained. Somehow we need to we are allowed to do the reaction, most of the reaction, not all, but in many reactions, these pi electrons actually they are removed also. But in most of the reaction, in many of the reaction, it happens in such a way that the reaction occurs and the pi electron continue to remain on the ring, right?
Sure.
Clear. So first of all, so we are studying aromatic halides or aryl halides, means the halogen atom is directly connected to benzene ring. Aromatic groups, there are many other aromatic groups also, but the benzene is the most common. That's why we are studying benzene halides, preparation of benzene halides. So how do we need to do it? So this is the general mechanism. Okay. If you want to attach not only to halogen, this mechanism is valid for nitration, for sulfonation, for any other aromatic reaction. So what this reaction is saying us. So whatever you want to attach to benzene ring, bring it as an electrophile. Suppose if I want to attach Cl, and I will bring it as Cl minus. If I want to attach Br, I need to bring in somehow. It is not actually, it doesn't exist actually. Cl plus or Br plus, they don't exist. They are not stable. But somehow in the reaction, I need to create them, and then only I can connect them to the benzene. CH3 plus, if I take, the CH3 plus can come and react with the benzene. Okay, and suppose if you want to attach the nitro group, so nitro group is available in NO2, NO2 plus, NO2 minus. So if I want to attach this NO2 group to the benzene, I need to have NO2 plus. Okay. So why we are so much obsessed with this plus charge? Why we need to have this plus charge? What is the reason?
The ends of benzene are electron rich.
Yeah, first, yeah, exactly. So this benzene is like a donut. Okay, because the donut actually that the pi electron join and they form a donut like ring above and below the benzene plane, molecular plane, and it is like a donut of electrons. So first of all, who can come and join itself to this donut? Who can get the electron? So the species which is electron deficient means which is electrophile, electron having species. So suppose if you want to have nitration or if you want to have alkylation, okay, if you want to have halogenation, first of all you should think in your mind that you need to have that thing in the form of plus or electrophile. Okay, so how this happens, I will tell you the general mechanism which is applicable throughout the organic chemistry in all the coming chapters. Okay, so you take electrophile, and what this electrophile will do, this will come and snatch the one electron pair out of the benzene. I will write here. Okay, and what will happen, you will have this kind of a situation in which H was already there. It is there in fact on all the atom. Just I have shown one H to because will be used later on. So this pi electron cloud, which was the part of the benzene, this has been snatched away by the electrophile, and now you have a plus charge. Electrophile was earlier, before joining itself to the benzene, it was plus, but after taking electron, it has become neutral, and the plus charge has appeared on the benzene level. And this is an intermediate stage because it is not stable. That we know, it is known as sigma complex. Though it is resonance stabilized, this plus can snatch the pi electrons which are ahead of it on the left hand side. Though it is resonance stabilized, but still it is not as stable as the original benzene ring, because original benzene was having 6 pi electrons and they were moving in cyclic manner because three pi electrons were there, right? Similarly, you can have this, right? And finally, what happens is, so it is not, so this is known as sigma complex or Wheeler intermediate also it is called by the name of the scientists who studied it. And this is not going to stay as it is because this is still not aromatic. Okay, we need to get back the benzene, neutral benzene with 3 pi bonds. So how we will get back? Someone who comes along with the electrophile, there should be something. You can't have only positive in a reaction. You need to have some base also, some minus also. So that minus will come and it will not, unlike what we have seen just now, where the minus were getting attached to the plus. That's what we have seen in Markovnikov addition. But in this case, it has taken place in a new way. The minus species which is there in the reaction, that doesn't come and join itself to the plus, but it takes away the H plus along with it. This is called base. Why H plus, and what happens to these electrons through which the H plus was connected to the benzene?
It will form the double bond, and
yeah, they will get back into the ring. The ring, your ring is retained. Okay, yeah. So this is what? This is a substitution reaction because H plus is substituted by E plus. And because it is, who is responsible? electrophile is responsible, so that's why it is known as electrophilic substitution reaction, and because it is taking place on an aromatic ring, so it is known as electrophilic aromatic substitution reaction, EAS, which are the most common reaction which occur on the benzene. Okay, and nucleophilic aromatic substitution also occurs, but they are difficult. They require very strong conditions because benzene doesn't want to invite nucleophile. Okay, they also occur, but at a very high temperature. But normally, EAS reaction happens. Okay.
Yes, sir.
So suppose if you want to attach Br or if you want to attach Cl, you need to convert them into Br plus or Cl plus. And Br plus and Cl plus, how will you make? You will take some reagents which contain Br, and the most common reagent is Br2, bromine, which is, and you take some Lewis acid. What is Lewis acid?
Electron rich species.
Electron deficient. Electron deficient. So I will make an empty box here. So Lewis acids are electron acceptors because they have the empty or vital on them. Okay. So Lewis acid are FeBr3 or FeCl3 or AlCl3 are Lewis acid species. Right. And what happens here is, if you take a Lewis acid, this lone pair Br2 is having a lot of lone pair. So the Br lone pair will come and join itself to the iron. So you have this kind of arrangement, Br plus, okay, Fe Br3. So you have plus, you have minus, and this breaks. And how it breaks? The Br plus takes away the electron, and the leftmost Br comes out at Br plus. That goes and attaches itself to the benzene. Okay. So see how it is happening. You can write the mechanism. Right?
Yes, sir.
So you can see chlorine you have taken, FeCl3, or you can take a Cl2Fe also. Sometimes this is also written. So you need not to worry about how we will get FeCl3, because chlorine and Fe react and they give FeCl3, which act as a Lewis acid. Okay. So either you can have Cl2FeCl3, Cl2AlCl3, Cl2Fe, one and the same thing. So one chlorine lone pair is taken away by the iron gets minus Cl plus, and this undergoes cleavage, heterolytic cleavage, and you get a positive charge on the Cl and FeCl4 minus. This is the electrophile which we called as E plus. That was the general way of representing an electrophile. Okay, and this E plus is going to go and attack on the benzene by taking its one of the pi electron. The benzene have a positive. This is going to be a difficult part of the reaction. So this is a slow step, rate determining step. It is a difficult step because the neutral molecule benzene is being attacked by an electrophile, and due to which it is not now temporarily it has not remained aromatic. Okay, this is sigma complex. Though this sigma complex can undergo resonance, but it is not as stable as benzene, which was completely neutral and complete cyclic resonance was happening. In this, the resonance can happen only in this portion where the double bonds are there. Okay. And this sigma complex is not going to stay for long because it is not aromatic. So what is going to happen? So we have UCl plus. A reaction can't have only plus there need to be someone who is minus. So that minus species come, and now it will come and breaks away the H plus. Okay, the Cl minus will come out from FeCl3 and it will break away the H plus from the point where the Cl plus was connected, and these electron will get into the ring and you will have it. So you will have HCl and FeCl. And this reaction takes place in dark. Do remember this. And this is electrophilic aromatic substitution, right? So if someone asks you what happens if Cl2 is taken with light in the benzene, so what happens in, suppose if you take Cl2 and light, you can also write that. Light or HU. Actually, light gives energy for the breaking of these pi electrons as well as Cl. So in this case, what happens? All the pi electrons break, all the Cl break, and you will have 6 Cl atoms connected to the benzene. And this is known as benzene hexachloride, right? BHC. It is also known as gamexine or lignane, which is used as an insecticide. Okay, is it clear?
Sure.
And is this a substitution reaction or addition reaction?
Addition reaction, sir.
Yeah, this is addition reaction. Exactly. So, but if you want to attach only one Cl or one Br, you need to carry out the substitution, and that substitution is carried out by taking Cl2 along with Lewis acid, which helps in breaking of Cl-Cl bond in a way such that Cl plus comes out, Cl plus goes is the active species, which is an electrophile. It comes and attacks the benzene ring, okay, and it forms a sigma complex, and from the benzene ring H plus is removed, and the Cl plus will continue to remain, and that's how you have chlorobenzene. Okay, right? So this is the general mechanism. Not only for chlorination and bromination, it is there for the nitration also. Okay.
Sir, these substitution reactions will always be carried out in Lewis acids.
Substitution, no, not necessary. Actually, that depends actually on whom you are doing the substitution. Substitution reaction on benzene, it is carried out in the presence of Lewis acid. But Lewis acid is just used to generate the electrophile. There are other ways also to generate electrophile, but in many you use Lewis acid, but not in all the reactions. For example, if you need to prepare nitrobenzene, you take nitric acid. Okay. Okay, that is a common acid which is there in our lab. You take nitric acid and you take H2SO4. H2SO4 is a very strong acid and it absorbs water and it removes OH. Okay. So OH is removed, so you end up with NO2 plus, which is an electrophile, and the same thing happened with NO2 plus. It goes and form a sigma complex. H plus will get removed, and you have that nitrobenzene. Okay, so it is not that always you take Lewis acid, but you need to make sure that if you are doing an electrophilic aromatic substitution, you need to generate that electron. Okay.
Yes, sir.
Yeah. Now the other thing is, suppose if a group is already present on the benzene, then where do we need to put that electrophile? Okay, where do we need to put? Suppose if in the last question we discussed that we were having benzene and we took Cl2 and we took FeCl3, and if someone asks us where will you put that Cl, I will say it is needless to ask because it is a regular hexagon. Benzene is a regular hexagon. You can put Cl anywhere on any of the carbon. It is one and the same thing. right?
Yes, sir.
But this is not the case in these three examples. You can't put Br plus anywhere. Okay. Actually, the group which is already present controls where the next group is going to attach on the benzene. Okay. A group which is already present, it controls where the next group is going to attach itself. And this is known as orientation. And it also controls the rate. So orientation and reactivity. So any idea what is going to happen in this?
It will attach at the ortho and para positions.
Yeah, very good. Ortho and para. So how you decided ortho and para?
Because they will be electron rich by resonance.
Yeah, exactly. And so this is ortho and para. Yeah. And what about this one? On toluene is orthopara-directing. What about this one? Bromobenzene. That also is orthopara.
Para.
Yeah, orthopara. Because what you can do is you can get an idea that we have seen that the 3 pi bonds were actually circulating in the benzene, and that's why it was called aromatic. It was very stable. Okay. So what happens if you have an atom with lone pair just outside the benzene? Okay, that atom is also invited into resonance. Okay, so what happens here is the p orbital of the bromine, the p electron, they can get mixed up with the electrons of the benzene. Okay, right?
Sir.
So, but actually that is a orbital picture. So, but we need to draw one by one to show that, okay, how it is happening. Okay, that is an orbital picture. That is an advanced way of thinking, and the more basic way is like this. Show one by one that how the electrons of bromine, lone pair of the bromine are getting into the benzene. So let's bring this electron into the ring. So Br will become plus and this will become minus because these electrons need to get shifted aside in order to make space for the incoming electron. So you have minus charge in ortho and para position. So this is also ortho para. And what about this one?
Same thing, sir. Ortho para.
No, there are two types of nitrogen. Okay, this is meta directing. Okay. So what is the key to find out? Look here. So what you said for the toluene was correct. Methyl was electron donating group. And how and what kind of electron it was donating? It was not having any lone pair, but it was having the electrons in the CH bond. And electrons of the sigma CH bond can get into the ring, get into the delocalization with adjacent pi bond, double bond. And this phenomena is known as hyperconjugation. Okay, it is similar to resonance, but not resonance. Okay, it looks like resonance, but it is not resonance because the one kind of electron which are getting involved are the sigma electrons. Right, so it is known as hyperconjugation. So you can see these electrons will get into the ring and it will get shifted. Okay. So and this will make the electron density of the CH bond will appear on the ortho position, para position, and ortho position, and that's how it become more rich. And that's why suppose if you have a Br plus which is being generated with the help of a Lewis acid and Br2, if someone asks you where the Br plus will join itself on the toluene, So it will join itself at the position where it can get the electron most easily. And you can see that because of the hyperconjugation, the places from on that ring from where you can get the electron most easily are the ortho and para positions, right? So that's why it is ortho para. And why bromine is ortho para? So all the groups which are having lone pair, their lone pair groups directly connected to the benzene, just outside the benzene. If they have lone pair, the lone pair will get into the benzene, shifting aside the pi bond of the benzene. The pi bond will get shifted to the ortho position, and that's how it will continue to move at the para and ortho. Okay, so all of those groups like NH2 is there, aniline, that also has lone pair. Okay, phenol, that also has lone pair. Anisole, that also has lone pair. So all these lone pair containing groups are orthopara directing for electrophilic aromatic substitution. Okay, and the methyls are also orthopara directing. Alkyl groups are also orthopara directing. But what about NO2? There is a difference between NH2 and NO2.
Sir, for bromine, we call it resonance, sir, or that also is hyperconjugation.
For if you use lone pair, that is called resonance. If you use loose electron, that is called resonance. If you use lone pair, that is called resonance. But if you use sigma electrons if the sigma pi conjugation, sigma electrons getting delocalized with the pi bonds, okay, that is called hyperconjugation, right?
Yes, sir. Yes, sir.
So what happened to NO2? NO2 is not like NH2. There is a difference between them, and the difference is very, 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 very huge. So NH2 has ideal lone pair, which where that lone pair will go, that will get into the ring, and that will make the ortho and para positions more electron rich. But what about nitrobenzene? So nitrobenzene, if you look at the NO2 group, it is like this. First of all, there are no lone pair available on the nitrogen. Instead, you have a positive charge. So the movement of electron is not going to be like this, which was happening in aniline. Okay. This was plus R effect. Actually, the NH2 was giving its lone pair, right? By resonance. So this is actually somewhat different. It is just the opposite. This cannot happen at all. You don't have any lone pair available on the nitrogen. Instead, you have a positive charge. So all the groups who do not have lone pair, instead they have double bond. Listen very carefully. If they have double bond and a more electronegative atom sitting at the other end of the double. So what this group will do? They will pull the electron density of the benzene out in resonance. So okay, this pi bond, it was in the ring and it moved like this. Nitrogen is a second paired element. It can't make 5 bonds. So if the electrons are coming from inside, we need to shift the double bond oxygen pi bond to O. Okay, you can see this. This is now minus. This is still plus. And where this plus will go? This plus is not going to sit here. Actually, this is going to pull the pi electron which is ahead of it like this. This pi electron, I will remove from this. I will make it like this. Okay. I will make it like this. And here the plus charge, next plus charge is going to come here. Okay. Yeah. So that's how it has happened. So actually we are showing them one by one, but electron is not actually that they come in, then they go there, then it is just the electron cloud which is somewhere it is more, somewhere it is less. So actually you need to draw the average structure, which is known as hybrid, resonance hybrid, which is actually derived by looking at all the structure by taking the average structure of all of them. So what conclusion can I draw? This is the conclusion. So suppose if somehow I generate Br plus by taking Br2 and FeBr3, where this Br plus will attach on itself on the nitrobenzene. Will it attach itself to the ortho and para positions? Br plus, where already you have plus charge?
No, sir.
That can't happen.
Meta
Because
position.
yeah, meta directing. So this is meta directing. Okay, electron withdrawing groups are mostly meta directing, not all.
Can you say the definition for electron withdrawing group again?
The group which pull electron by resonance. The group which exert minus R effect. I will give you a list of all the groups. Okay.
No, sir, you said right. It is having more electronegative group.
Yeah,
And,
normally these kind of groups. So you have a double bond and there is more electronegative atom at the other end of the double bond, which will pull the double bond, and that's how the group will pull the pi electron from the ring. Okay. Sometimes without double bond also there can be electron withdrawing group like this one. The groups which have positive charge. This doesn't have any, this tertiary quaternary ammonium salt doesn't have any double bond, but still it is very strongly electron withdrawing because there is a positive charge on it. So groups which have positive charge, which have electronegative group bonded by double bond, they all are electron pulling groups and they are meta directing. And the groups which have lone pair, they are ortho para directing. Okay.
yes, sir.
Clear. So if I join the Br, and suppose one more thing, is the reaction going to occur faster than the benzene or slower than benzene for nitrobenzene? So I can put it in another way also. Is the nitrobenzene an activated ring for electrophilic aromatic substitution, or is it a deactivated ring for electrophilic aromatic substitution? If it can react quickly faster, then it is activated as compared to benzene. But if it is reacting slowly, then it is deactivated. So how will I judge? How will I decide? On the basis of electron density. You need to look at the electron density. Is it increased or decreased? Is the electron density sucked out of the benzene or is it pumped into the benzene? By NO2 group. Yeah. Yeah, it has been sucked out by NO2 group. Look here, minus R effect, minus M. Okay, you can use any of them to say. It has been sucked out. So zinc has become electron deficient. So if the electrophile will come, electrophile will feel very difficult to join itself to a ring which is already electron deficient. Okay, so this is a deactivated ring. It reacts million times more slowly than benzene. Okay, million times. On the other hand, aniline react million times faster than benzene, million times faster. Okay.
Yes, sir.
So you can revise. Revise more through NCERT. Which book we are following right now?
NCERT, sir.
Yeah. So you can read and go through it. Let me know if there is any doubt, and next time we will discuss more important things. Okay. Some more questions. Some more ways to attach halogens apart from these electrophilic aromatic substitution.